Historically, computer simulation techniques went through the following stages of development. In the 1940s, analog simulation was the major way of simulation. Digital simulation began in the 1950s, and in the 1960s, the first simulation languages and packages began to emerge. In the 1980s, the development of object-oriented simulation techniques was the leading trend. With the popularity and wide availability of digital computers in the past 30 years, a great many professional computer simulation languages and tools have appeared, such as CSMP, ACSL, SIMON, MAT-LAB and Simulink Matrix X, System Build, and CSMPC. Because MAT-LAB and Simulink have become more and more popular and powerful, most of the above-mentioned simulation packages are no longer available. MAT-LAB and Simulink have become the de facto standard computer language and tool for system simulation. Model-based design is a mathematical and visual method that facilitates the complex design of embedded systems. Instead of using extensive and complicated programming codes, designers can use MBD to define models with advanced functional features using continuous time and discrete time simulations. The main components of a model-based design are system-level and component-level design and simulation, automatic code generation, continuous testing and verification. In the past, running the system in simulation or running it in hardware were the only practical alternatives for many engineers seeking to deploy their control systems. In recent years, two alternatives have become common: rapid control prototyping, also called RCP, and hardware in the loop, or HIL. In RCP, the control laws are designed in a simulation environment and executed on real-time hardware, driving a physical power converter and plant, and reading physical feedback sensors. In HIL, the plant and feedback sensors are simulated, while the control laws and signal processing, such as filters, are executed on the target hardware, whether that is an embedded controller or a PC running control laws in real time. The MBD begins with the MIL scenario, which consists of developing models submitted to simulated test environments at the beginning of the design. The models are then refined and transformed into software. These software can be tested in the SIL scenario or in the processor in the loop scenario. Finally, the HIL scenario contains the real hardware and software integrated into a simulated environment. RCP can be used to facilitate concurrent development of control systems. Consider a project where the control system and the plant are being developed at the same time. Further, consider that the plant may be so complex that it might be developed in stages over an extended period of time, so that initially only a small portion of the plant may be available. RCP can be used to deploy the control laws to available hardware, while those portions of the plant that are not yet available can remain in simulation. RCP can also be used to isolate critical hardware, which can reduce test time, improve safety, and expand the test coverage. Consider the testing of an anti-lock brake mechanism, where the mechanism itself is RCP, but other dynamics, such as vehicle suspension, pitch, and the effects of the road surface, can be simulated. Compared with testing the full system in a vehicle, the RCP technique allows the mechanism to be tested quickly and inexpensively over a broader range of conditions and with fewer safety issues. Since the control laws are operating on the actual plant, the possibility that inaccurate models are corrupting the results is removed. RCP allows a three-step process of migration. First, full simulation at the start of development. Designers typically simulate the entire system. Second, when the design is sufficiently mature, the model of the simulated hardware can be replaced by actual hardware using RCP. The control laws designed in the simulation environment are executed in real time on commercial off-the-shelf hardware, for example, PCs in the lab with a physical power converter, plant, and feedback sensors. Third, when operation in RCP is sufficiently verified, the control laws can then be migrated to the embedded controller with the right toolchain. Engineers can reuse the algorithms designed in an earlier phase for this final step of the development process. Hardware in the loop, or HIL, is in a sense the opposite of RCP. The control laws are deployed to final hardware, while the power converter, plant, and feedback sensors are simulated. As with RCP, the simulation must be executed in real time, because part of the system here, the controller, is physical hardware. Also, there must be hardware to interface to the control law, output, and feedback sensor signals. The HIL scenario tends to become the standard electronic development tool for testing ECUs, MCUs, and particularly their software for different OEMs. HIL has been used for years in industries such as aerospace and automotive, where plants are especially complex. HIL can augment testing of physical plants to provide many advantages. This video is just an introduction to real-time simulation, RCP and HIL. Over time, we will present many more systems and applications. Thank you.